hear me? No, eh? Okay. Can you hear me? Okay. Okay, thank you all for coming to this Friday talk. I have the great pleasure to introduce you to Konstantina Agiadi. She's a good collaborator of our group and has been visiting ECM now for some years with Marie Curie and now with different projects that she has. So I'm going to read my notes. So she works with the interaction between climate connectivity and marine ecosystems of the past with the aim to inform present and future conditions of marine ecosystems. She has an undergrad in geology at the University of Athens in Greece, also a master's in paleontology and stratigraphy, also in the same university, and a PhD in geology and geoenvironment with a thesis on paleoecology and paleoenvironmental reconstruction in the Eastern Mediterranean Sea. She's currently at the University of Vienna, leading several projects on reconstructing ancient marine food webs and developing biogeochemical proxies. And she's currently leading the PHS working group, Kumares, that is called Disentangling Climate and Pre-Industrial Human Impacts on Marine Ecosystems. And she's also leading the very new cost action Salt Ages. So Konstantina is going to explain her work, especially a recent paper that she published, and I would like to thank her for coming today, and the floor is yours. Thank you.
Thank you, and I would really like to thank Marta for inviting me. This is a great opportunity to show what we recently did and to meet everyone. So I just realized before this that as a geologist, when I look at this, I see, nice marine sediments, and we can find lots of fish bones in here and shells. But then, for marine scientists, this looks like land, which it is, but yeah. So this is a nice outcrop on Crete, actually, where we found sediments. These are clastic sediments with lots of fossils inside that were deposited in the Eastern Mediterranean before the Messinian Salinity Crisis, and this was the starting point. So what I do in general, I'm working in between geology and biology and ecology. I started as a geologist, but my interest is clearly marine, and my research is marine. And I work to explore how climate and connectivity in the past affected marine ecosystems, but also how the marine ecosystems affected climate and biogeochemical cycles. And ultimately, there is a two-way interaction there. So, what I want to show you is the three studies. Actually, these three papers were published this summer, and it was the result of one long study over 6 years to reconstruct the impact of the Messinian Salinity Crisis on the marine biota in the Mediterranean. And for those of you who don't know, the Messinian Salinity Crisis was the largest, the most important paleo-environmental perturbation of the Mediterranean Sea, because around 6.6 million years ago, the straits that connect around Gibraltar, not exactly at Gibraltar, but the straits connecting the Mediterranean to the Atlantic closed. So the Mediterranean became isolated and started to evaporate a lot, and became eventually hypersaline. And this resulted in the formation of kilometer-thick deposits of salt on the bottom of the Mediterranean, which we can find today through drilling. And this was discovered first in the 1970s when they first started to drill in the Western Mediterranean, and they drilled, and the core that came out was the recent sediments, and then at some point they hit salt, and they kept hitting salt, and it was a lot of salt. And even before that, we had observed around the margins, so where you can see like all these areas, the purple, this pink, essentially. There were areas also that were on land. You can find gypsum. And so we had an understanding that there was something going on around the age of this, around this age. But then when we found this huge salt in the bottom, then all the scenarios started to develop to explain how this happened. And then they discovered this closure of the straits was what caused this isolation and evaporation of the basin. And we can find the salt in all over. So you can see here, So you can see here the halite and the gypsum deposits are everywhere in the Mediterranean Sea. This event lasted from 5.97 to 5.33 million years. This is the interval where the gypsum and the salt were deposited, and this is the actual Messinian Salinity Crisis. But the events that led to this isolation did not happen overnight, so the closure of the straits started to happen already from 8 and from 7.2 million years. There was already quite a lot of restriction of the basin, which created problems for the marine ecosystems. And you can see here, so the straits at where today is Gibraltar, before the Messinian Salinity Crisis, there used to be this complex. There were different straits in South Spain, in North Morocco. There were different corridors. And the tectonic activity led to the uplift in this area, essentially, and close gradually first the reef, and then the Betic and the reef corridors, and eventually led to the isolation. And during this restriction phase, that was from the time when the isolation was almost, well, it was significant until the start of the Messinian Salinity Crisis, what the proxies, the biogeochemical proxies reconstructing temperature and salinity have shown at the surface and at the bottom, we know today that what happened was that gradually the inflow of water from the area in the straits became restricted, so that the Mediterranean could not circulate the water. The water inside the Mediterranean could not circulate properly, and this led to alternating conditions of hypersalinity, but also hyposalinity, so fresh water, because we had a lot of input from rivers and from the area in continental Europe that used to be an epicontinental sea at the time. So these changes, this led to this interval, the 7.25 to the Messinian Salinity Crisis, was full of extreme conditions for marine organisms, where there were hot and cold temperatures, exchanging periods with very warm temperatures and very saline waters to periods of low and hyposaline. And then we had also the bottom waters became stale. They couldn't deoxygenated because the circulation was not as it is today. And you can see that during the crisis, so within the actual Messinian Salinity Crisis, there were also different stages where the first, we had so here. Sorry, here is the down is the first part. So there were gypsum deposited so there was still a marine basin, but with problematic, let's say, circulation, where there was still inflow from the Atlantic, but no outflow. So the strait had uplifted so that water could come in from the Atlantic on the top, but it could not come out. So there was gypsum then deposited in the margins. So these areas that are emerged. And then during the main part of the crisis, the peak of the crisis, where the straits were completely blocked, there was the deposition of the halite, of the salt. And then at the final part, there was influx, a lot of influx from this epicontinental sea that was the Black Sea and the Caspian Sea together with some other smaller basins, and this was flowing fresh water inside the Mediterranean and creating brackish environments. And then during the reconnection phase, so after the flooding of the Mediterranean with Atlantic water, their most recent scenario says the most recent data show that still the reconnection phase was not straightforward, so that even though we had marine conditions, the water that was coming in from the Atlantic was normal marine conditions, but it eroded the salt and created brine in the Eastern Mediterranean. So it was also, it took tens of thousands of years to bring back the conditions that were the normal marine conditions in all of the Mediterranean. So, and why do we care? Because, well, our Mediterranean Sea is our favorite ocean. It's a model ocean, so we care. And it's actually because this is a model ocean, we can study a lot of important phenomena in much smaller spatial scale. Today, it has more than 20% endemic marine species, which makes it a biodiversity hotspot. And there is a northwest to southeast gradient decreasing in species richness. And today, it's experiencing extreme climate warming, much more than other areas of the world, and also biological invasion after the opening of the Suez Canal. So this Messinian Salinity Crisis has been known since the 70s. And, well, why don't we already know what the impact was on marine biota, which is the main question that we tried to study over the past 6 years. And the problem is that although there have been important works since the 70s already, to reconstruct the fossil record of before the Messinian Salinity Crisis and after for different groups of organisms. And also there have been important studies finding the very scarce fossils discovered within the actual crisis, so within sediments deposited within the actual crisis. The problem was that all of these did not include a critical examination of the fossil record. So some studies, they looked at the literature but didn't actually assemble a database, a data set of all the published record, and didn't revise this, didn't examine the systematics and the synonymies, and this was record that was published from the last 150 years, so many things have been updated since, have changed. And also the most important thing was that until very recently there was very scarce knowledge. So the records of marine organisms, so fossil record from before the crisis and after the crisis, was very fragmentary. There could be some nice studies in the Western Mediterranean, but many parts of the Eastern Mediterranean were not studied at all. So it was really problematic that no one could actually say what happened to the whole of the basin. And importantly was, and what was the first thing that we did was, in the past, all the studies focused on only one group. So in order to find out what happened, what was the effect of the Messinian Salinity Crisis on the biodiversity, marine biodiversity, we took a step back and we said, okay, let's gather the fossil record from before the crisis and after the crisis and see what happened. So compare and see how biodiversity changed with very simple metrics. All the hard work was assembling the data set. And in order to do this, we gathered a group of experts in their own field, so experts in bryozoans, experts in dinocysts, experts on fishes. This is what I did, and on different groups of forums. And all these experts dug into the literature and collected the original publications with information about the locality, where the fossils were discovered, the age, which then had to be corrected because sometimes when someone published 150 years ago, they said, oh yes, this was inside a sediment, this fossil fish was discovered inside a sediment, and this sediment was of late Miocene age. And this is not very informative for our purposes, because late Miocene means 20 million years, but it also means 5 million years, 5.5 million years. So this doesn't help us. However, later on, like 20 years ago, maybe someone studied those same sediments in the same locality without actually looking at the fossil fish remains, but then they did a stratigraphic work, and they said, okay, these sediments are not 20 million years old, they are 7.5 to 7.2 million years old. So this, then we had to take the original publication and update this with information from the most recent publication to actually put it into the database. So this is all the work. This is why it took us so long. And then also we had to find, to confirm the identifications. And many cases, the experts, exactly because we chose them as experts, they had first-hand knowledge of the material, so they had visited the museums, they had seen the material, they could confirm that this was indeed the species that was identified, or they could say this was revised. So 150 years ago, the people did a great job, but then since then, we know more about the taxonomy and the systematics of this fossil group, so we can say this actually belongs to this species. On other times, they did not have first-hand knowledge of the material, but they had to rely on the photographs in the publications, and other times there were no photographs of the material, only descriptions, and in rare cases there were not even descriptions of the material. We gathered this information, and we actually put, during this stage, we could confirm, then we put a state of knowledge in the database so we can say whether it was from an expert or confirmed or revised, or if there were only from the literature. So just a reference that we could not confirm. And then, okay, we checked for synonymies and the systematic schemes and updated all of this. And then cleaned the database, of course. And then we assigned the localities in 3 regions, which I will explain later on. And after combining all this information, we came up with more than 23,000 presences of marine species. This includes almost everything. So this includes calcareous nanofossils, dinoflagellates, cysts, planktonic and benthic foraminifera, corals, bryozoans, echinoids, gastropods, bivalves, fish, and marine mammals. And overall, we have almost 5,000 species, and covers the interval before the crisis, so this stage that is called Totonian, from 13.8 to 7.25 million years. The part of the restriction phase that is from the 7.25 to 5.97 million years, and the part that is the Sanklian, that is after the crisis, from the 5.33, when the gateway opened again, until the 3.6 million years. We have this information was georeferenced, and all the taxonomic revision information was recorded as explained before. And the level of confidence in the identification was also indicated because, for example, there were fossils that were, someone found, for example, a bone of a seal, and they could say that it was a seal, but they couldn't say which species. So we still have this information of the family or the genus name, but the species name is uncertain, and we have recorded this level of confidence in the database as well. And this is now openly accessible and public, anyone can use it. And well, this is broadly what we have. As you can see, and I will show again, there are large differences between the regions and also between the groups. So there is a lot of sampling bias. And there are inherent biases in this data set. So first of all, there are presences in the fossil record that are recorded without any description, without any photographs. We have included them, and we have included in a state of knowledge that says this is the case, but we have not excluded them so far from the analysis, but this can be easily done, of course. Then there's important spatio-temporal gaps due to the uneven, due to many reasons, actually. One is geopolitical reasons. So the Northwest is much more sampled than the southeast of the Mediterranean, and this is clearly why. We can understand why. There are also, however, differences in the distribution of the outcrops. So the outcrops, such as the one that you saw in the first photograph, we cannot always find the outcrop of this locality that corresponds to this facies, which means you need an outcrop of shallow water sediments, so you can find the organisms that lived in shallow water, but also those that lived in deeper water, and of every single age, and that every of the groups was also studied. And this is not always possible. The fossil record in general favors organisms that leave a very robust skeletal material. So larger specimens are favored. It's much easier to find, for example, I don't know, a chlamys or a bivalve that is quite robust than it is to find a pteropod, simply because it's more fragile. And there is still, in some cases, there is insufficient stratigraphic framework. So in some cases, we can find a fossil that is mentioned as Pliocene. And this is, again, is not very helpful because it could be early Pliocene, which is what we want, or it could be late Pliocene, which is out of our scope. Then, in order to do the analysis, we assigned all the occurrences in 3 regions and 3 periods. So the 3 periods are the Tortonian, which is before the restriction, the Messinian, that is during the restriction phase, and the Zanclean, that is the reconnection phase. And the 3 basins that we divided were the Western Mediterranean, the Eastern Mediterranean, and the Adriatic, which includes the Po Plain. And this is now, today it's an important biogeographic region, but we wanted to test whether this was the case also in the past. And even though it was actually formed, it was separated before that, it was connected to the Western Mediterranean. So this here was connected. And this was disconnected in the late Tortonian and the beginning of the Messinian. However, we included also the Tortonian, of the record of the Tortonian occurrences within the Po Plain and the Northern Adriatic to make it uniform. We analyzed species and genus richness, turnover, and nestedness, the whole region, and by period, and we compared between regions and between periods using a classic rarefaction. And also we repeated the analysis separately for zooxanthellae and azooxanthellae corals, because this was an important group, as it turned out. And these were the first results. So this is just species richness. What we did here is, so this is a paleogeography of the Mediterranean when it was still connected to the Atlantic before the restriction phase. So it's a bit, I understand maybe it's a bit too colorful. So what you see here are the distribution of coral reefs. And also, so this here was closed, so And you see here the straits are quite wide, and they were wide but shallow. And these are the species richness by group, where this is after subsampling, and this shows the number of the species. And then what we did was use this as a baseline and said, okay, then in the restriction phase, what happened? And you can see that some groups had increases in species richness, whereas others had decreases. Most of them, there was decrease, but in some cases there was an increase in species richness compared to the Tortonian baseline. And then during the Zanclean, so during the reconnection phase here, again compared to the Tortonian baseline, where essentially what this shows is that there was a restructuring of the ecosystem because the organisms did not respond in the same way. And these are the comparisons of the three intervals, the Tortonian, this is the T, versus the Messinian. So before the crisis, compared to the restriction phase, is the first, is this one. And so the first in each box plot is this. And then the second is the restriction phase compared to the reconnection phase, and then the overall impact is the third in each one. And you can see here by group, and which shows that clearly there were many differences. Overall, what happened, what we noted was that the cooling that happened during this period was an overall cooling globally. And this cooling seemed to have affected temperature-sensitive organisms. This happened globally, and we also observed it in the Mediterranean. We do notice some boreal species extending their distribution in the Mediterranean, even within the Messinian. However, the relic species that were present in the Mediterranean even before the restriction phase, when the Mediterranean was still connected to the Indo-Pacific Ocean, these started to disappear because they were warm water species. It is possible that some species, endemic species, found refuge during the crisis in the Atlantic, in the small basins near the Gulf of Cadiz or in northwest Morocco, but the nestedness that we found was low in all comparisons. So when we compare the before the crisis to after the crisis, nestedness is consistently low, which means that the species that we have after the crisis are more likely new species from the Atlantic than re-establishment of species that existed in the basin before the Messinian Salinity Crisis. So the most astonishing effect was that the coral reefs that were extensive before completely disappeared after the crisis in the Mediterranean. However, the deep water corals flourished. And we also noted that in some groups, you see this here, for example, even though we have the crisis, you see an increase in all comparisons, in both comparisons, and here as well from the before and after the crisis. And this is because there were new endemics developed. So when we break it down by the groups, by the different groups for calcareous nanoplankton and dinocysts, we see that the species richness in the Western Mediterranean decreased, but in the Eastern Mediterranean, even before, so during the restriction phase, but it took some time. So in the Eastern Mediterranean, this happened only after the crisis. We observed this after the crisis. In contrast, for planktonic foraminifera, we see that the species richness decreased already in the restriction phase, but then rebounded. For ostrocods, we have during the restriction phase, these are very sensitive and they show these assemblages, their assemblages are low in abundance and diversity. And there is a drop in species richness after the crisis, but mostly in the Eastern Mediterranean. For bivalves, but also for fishes, we have also diversity loss in the restriction phase and recovery after the crisis. But for echinoids, there is diversity loss throughout. So even after the crisis, we never recovered the diversity that was before. And for azoxanthellate corals, for gastropods, bryozoans, and benthic foraminifera, there was an increase in species richness during the restriction phase. As I mentioned, the zooxanthellate corals were already affected by the late Miocene cooling, so that as the Mediterranean moved outside of the tropic zone, they were already affected, but then during the restriction phase, they became very decreased. They dropped in species richness, and by the Pliocene, we didn't have any coral reefs anymore. And larger animals like sharks and marine mammals, they follow global patterns. So what were the overall impacts when we looked at and what you see here is, so this is the climate reconstruction, so the sea surface temperature and salinity in the basin. So this is the interval that we have studied before the crisis. As you can see the large amplitude fluctuations, and this is after the crisis, right after the crisis. So the species richness dropped clearly before actually the crisis. So before the onset of gypsum and halite and salt were deposited, we already had a drop in species richness. So during the restriction phase. And after the crisis, there was some recovery, but even for the interval that we studied, that is up to 1.7 million years after the crisis, the species richness never fully recovered. So there is a net decrease of 8% that was never recovered, at least not within the time that we looked. And these patterns were mostly driven by the Western Mediterranean, whereas in the Eastern Mediterranean, the species richness continued to decline even after the crisis. So there was no recovery. So most taxonomically, the biota comparing between before and after the crisis, and were 66% dissimilar, and even most of this happened during the restriction phase. So when we compare so this would be, here, if you see that during the fauna before the crisis, before the restriction phase, and compare it to the fauna during the restriction phase, these were 50% dissimilar already. And we have very high species turnover, and low nestedness, which means that most of the introductions were new species coming from the Atlantic. So, and this is exemplified now with endemics, that we recorded all the endemic species in the Mediterranean during the restriction phase, so before the crisis, and we found almost 780 endemic species, and from those, only at maximum we could not track 86 that could have survived the crisis. And finally, we found that the northwest to southeast decreasing trend in species richness that we observe in the Mediterranean today first appeared after the crisis. And this is astonishing because the Mediterranean as a basin did not exist before the 13.8 million years. So before that, the Mediterranean was connected to the Indo-Pacific Ocean, and the straits were quite wide. It was part of Tethys. So as a notion, as a concept, it did not exist. As a distinct paleogeographic space, it started to exist after this time. And from the 13.8 million years until until the crisis, so until 6 million years, there was no gradient in species richness. This means, but this gradient developed after the Messinian Salinity Crisis. So all of these million years, there was no gradient, and then immediately we have it after. And what this means is that we can say that perhaps also today, this gradient does not exist because the only source of species is from the Atlantic. So this is not the reason. Also, the configuration of the basin was the same. Still, the Eastern Mediterranean was warmer, was had southern parts than the western, so there were parts that were warmer. So again, the temperature is not the reason as well. We don't know what the reason is, and also we cannot say with our data whether this gradient continued after the beginning of the Pliocene. So after the 3.6 million years, that is the interval that we studied, we don't know if this was reversed in any way or reestablished. We cannot say that. But what we can say is that the reason is not the connection to the Atlantic, and it's not the temperature. And to bring to a bigger context, so here you can see all the main evaporatic basins, marine evaporatic basins that have been found by geologists around the world. And the color just indicates age, so these are billions of years old, coming to the most recent. The Mediterranean, these are called salt giants, and the Mediterranean salt giant is this one here. It's one of the most recent, but it is the best studied one. And what we show is that what happened, what we showed with this study is that the formation of this salt giant was an important geological event, and it had an impact on the marine biodiversity of that basin, but it must have had an impact also on the basin, on the global biodiversity. And this is because, as I mentioned, the Mediterranean today has 20% endemic species, and we saw that this was the case before the crisis. So, and these species, most of them disappeared. So there is a loss of biodiversity when you desiccate a basin like this in order for a salt giant to be formed. And there is also the fact that when this basin is isolated and water is evaporated, the salt that precipitates is taken out of the global ocean. So there have been previous studies that show that during the Messinian Salinity Crisis, the salt that was kept within the Mediterranean because of the crisis reduced the global salinity by 5 per mil. And this is important because it took 5% of the global salt from the ocean. It was taken up by the Mediterranean. And this is important because a reduction in global salinity also has an effect on marine organisms. So our next step would be to see if the other salt giants had the similar impacts on marine biodiversity in their own basins, but also globally. And this is interesting also because the formation, as you can see here, the ages, so the formation of salt giants is something that happens recurrently throughout geological history. So it's not a very unique phenomenon, even though our Mediterranean salt giant is very unique, but it's something that happens again and again. And it is associated with the opening and the closure, the formation and the death of the oceans. So when you have a new ocean forming, the tectonics that lead to the formation is very easy for that to result in isolation of basins, of marginal basins. And the same when you have a closure, so when the ocean, the two plates come close so that the ocean is dying, then it is very easy to have marginal basins that have become isolated, and then you can have a salt giant. And to bring this into more to an ecological context, this falls then with the concept of this marine functional connectivity. So essentially what happens when a salt giant is formed is that it disturbs the natural patterns of connectivity between populations, from between the coastal and deep waters, between the land and the sea also. It prevents seasonal latitudinal migrations from large marine animals. It destroys the patterns of vertical migration because it alters the depth distribution, the paleo depths. And it prevents, in cases when you have the gateway restrictions, then it also prevents plankton and larval dispersal. And so we can use a lot of different geological and paleontological and biochemical information to find evidence of this. But this is what we expect that happens when you have also a salt giant, an isolation of the basin, and then you have a salt giant formed. And what we finally did was we came up with this conceptual model where we know that the tectonics and the sea level changes create the gateway, lead to the gateway dynamics. So when you have a connection or disconnection of a basin, and during the restriction phase, which in the case of the Mediterranean salt giant would be the pre-evaporating Messinian, those what we call the restriction phase, and the first stage of the actual crisis, when we had only Atlantic water coming in. So this would lead to physical changes in the basin, within the basin. So the simplest is the reduction of the silt depth, which then leads necessarily to a loss in connectivity at depth, because you can't have organisms that would move from the Atlantic to the Mediterranean and backwards at depth. They can no longer move. And then we found evidence of this was the dissimilarity in bony fishes, which actually, looking into the database, it actually has to do more with deep water fishes than it has to, it's not coastal species. And similarly, other changes lead to the water column stratification, which and the anoxia depth, which leads to extinction of deep water animals. And then when we have the closure, the final closure of the basin, then we have a drawdown. So the level of the basin draws down. This leads necessarily to transformation of the coastal habitats and problems for population connectivity. And also we have the immigration of brackish species from the rivers, but also from, in the case of the Mediterranean, from adjacent seas, adjacent freshwater basins. And during the opening, so when you have the reconnection with the global ocean, there is a forced influx of larvae and individuals, so you have a flood, which brings a lot of individuals, but this does not mean that they necessarily form populations. It takes a long time for them to form, to establish populations. And so this is why we have, for example, a delay here from the flooding to the forced influx. So you can see the times here. And finally, that was it. I hope you were not so tired. And I would like to thank Marta and Danielle also for this work. It was very important for me, their support and their inspiration. But also all the collaborators that provided important insight and expertise in the different groups in order to form the database, but also in the analysis and the interpretation. And last, thank you. And this is the logo of our new construction. And you can join, the link is here if you are interested to see more.
Okay, thank you very much, Konstantina. It's very inspiring, and I always think that Konstantina's work is a clear example for me is when they tell you, oh no, this is impossible, and somebody comes and does it. So that's really, really inspiring, at least for me to collaborate with Konstantina all these years. Any questions? Don't be shy. No?
Thank you for the talk. Probably you know that there are different theories about the isolation or no of the Mediterranean with respect to the Atlantic. The traditional is that there was complete isolation. The second is that it didn't occur. And the third is that it occurred at the end of the Messinian Salinity Crisis. There are different proxies, different groups supporting the different theories. And I think that with this work is supporting the traditional scenario.
Well, yes, what we found, actually, yes, it does support the original scenario, but I would like to stress that we took the fossil record before and after the crisis in order to see, to make something that is robust. So we did not include the interpretations, so we disregarded the interval that was exactly at the salinity crisis because the fossils that are there are not enough, were not enough for this kind of statistical analysis anyway. So this is what we found, and yes, it does support the original scenario.
Okay, with respect to the thickness of the salt, the average in the deep basin of the Mediterranean is about 2 kilometers, but in some points, I think that it reaches about 3 kilometers, but it's not a huge layer. It's a level with different cycles of salts. That means that there was water, or there were different water inputs during the Messinian Salinity Crisis.
Yes.
Have you detected something with these different inputs? Nothing.
No, but
Not
we
really.
didn't look at the fossils that were found within the crisis itself. So we excluded completely the interval 5.97 to 5.33. We included nothing from there.
But even in the paleogeographical scenarios around the Mediterranean, because there are some people that say that water is coming from the Atlantic or coming from the Black Sea, there are different entries. And even before, just before, or nothing.
So there are, yes, there is a scenario that there are several publications that show that there was influx from the Paratethys at 6.1 million years. Yeah. And this is an explanation for some of the patterns that we see in the Eastern Mediterranean. For example, the difference in calcareous nanofossils and dinocysts, that we have a different response, so that we have the decrease in species richness in the Western Mediterranean during the restriction phase, whereas we have this drop in the Eastern Mediterranean after the crisis. And this possible explanation is that the richness was maintained in the Eastern Mediterranean during the restriction phase because of the influx from the Paratethys during that time. But of course we cannot know for sure, but yeah.
Okay, probably it's interesting to go through that period in order to support the other theories.
There is still work to be done, yeah.
Probably you have the key. Okay, thank you.
Thank you.
More questions?
Thank you. Great talk and huge amount of work. I can imagine that. Can you confirm, I understand that you are only looking at terrestrial cores, so you are not looking at marine actual sediment, right? So everything is outcrop and in land.
No, we included everything, but so we included also the records from the cores that are available, but everything that is publicly available, of course. If it's not published, we couldn't. But these are only for microfossils, of course, because unnecessarily for the record for the for fish or for marine mammals is only from the land. Yeah.
That's right. So that was one of the questions regarding my second comment. I would like you to comment a little bit more. You already mentioned that you're going to have a bias because first what you find in the sediments, so you are only looking at things that leave a fossil record there. Yeah. So I would like you to comment a little bit on that. And also, how do you think this could affect the fact that in some places you may have a larger or longer record or more wide record of different organisms, and in other places you only look at microfossils, for instance, that it could be the case in the sea. So just a brief comment on how you did that, or how you manage with this different data set, right?
Yes, so because we compared within the basins. So we compared the different regions within the basin. So we compared the Western Mediterranean to the Eastern. We did not look at what happened within the East, within the Western. So there are cores from the East, the cores from the West. This was the same. And there are differences, but in the sampling effort, of course, and what we find. But then the 80% subsampling is a standard method that it's very good for compensating for this. So yes, I mean, in the future, if we find more records, we can improve always, of course. But for now, yeah, this is what exists.
Yeah, just a quick question. Regarding corals, you mentioned that before you had tropical corals, that they just disappeared, right, after the Messinian. But what about deep sea corals? Deep sea corals, you said that they flourished afterwards.
So we had, yes, they had, there are many species after, so deep water corals, they were fine. But the reef-building tropical corals that existed before, we don't find them anymore after the crisis.
And deep sea corals before the crisis?
Yes, they existed, but then they were even more after more species after the crisis. Yes.
Mm-hmm. Okay. And any reason for that? Where did they came from? The Atlantic or the
Well, yes, probably
all of them.
Some, but yeah.
Okay. Good. Thank you.
Any other question? Okay, I want to stress the fact that this database that they built, it's open access, so you can go figure out which corals are there, and so that's I think part of the beauty of this work, no? That after 6 years of hard work, it's available for everybody. So,
and the code is available as well. I mean, the database available, we can add to it more new records and run the code again and see what happens.
Salt Ages project, what's about?
So the Salt Ages is the new cost action, and it has many objectives. So it has groups on the biological and climatic impacts, which is what I would like to do is do similar things in other salt giants in the past, which would be also very interesting. And there are also there's a working group on salt and humans, which goes from archaeological importance of salt of these particular salt deposits and to the industrial applications. There is a modeling working group, and there is a big picture, so trying to understand how the plate tectonics is connected to the formation of salt giants throughout geological history. And we have also a working group on public engagement and education, because that's also important there are many geoparks around Europe and museums, natural history museums that can exhibit this kind of information. So yeah, we just started, and it's open to anyone.
Nice. Thank you very much, and thank you, Konstantina, for your time.